Cool. Right, afternoon everyone. Hi Chris. Cool stuff. So this is a little bit about how we manage the infrastructure at Redgate. So first of all, quick intro to who we are, IT operations. John, who sort of keeps us all in check. Amanda, who looks after licensing, purchasing, that sort of thing. That basically means dealing with a few thousand different types of software from a few hundred different suppliers and all the license agreements and everything else like that. Vicky, Steve, Mo, who are the ones you're probably most likely to have met. They're the ones that come and make sure that everything's working at your desk, make sure that everything's ready for new starters, make sure we kick you out when you leave the company, that sort of thing. Generally, not going to talk too much about what these folks do today. More focusing on the four of us. So this is Nick, Simon, Nika, and myself. And we generally focus on the infrastructure side of things. Now, that's a fairly broad set of services. That's internal-facing things like keeping Sage going so that everyone gets paid. It's external-facing things like the Redgate website. Build system, test system, some of it's customer-facing, some of it's not, keeping the network going, making sure that phones still work, all of that sort of thing. So what does infrastructure actually look like for us? Well, there's a little bit of this. So a small amount of it is moving around bits of metal, putting new servers in racks, shoving your head into the floor when you're trying to find where a network cable appears in Mubanellis. But again, that's actually a pretty small part of what we do. So out of interest, anyone have a rough guess at how many servers we run? Finger in the air estimate. Ali? 7. Piers? 40? Yeah. 42. Meaning of life. Okay, so as a clue, the stuff that Simon just talked about in the last talk is probably about 10 servers. I'm not sure exactly, because I didn't count them, but it's about 10. Actually, it more looks like that's 140. There's another 40 or so that aren't on there. There's a bunch more stuff that isn't managed by Puppet. And that's not counting all of the external infrastructure and software, the external software as a service, platform as a service stuff that isn't managed like that. So it's somewhere in the hundreds. We don't kind of have an exact number on it because it doesn't actually matter. Of that 140 different servers, there's about 75, again, don't know exactly, about 75 different things that they do. So on average, for any given task, there are about 2 servers that do the same thing as each other. All of that means that there's quite a lot of systems and not that much time. There's 4 of us that look after that stuff. And so a lot of the time, our goal is to maximize the time between attention needed. Yeah, if we were to run these things where every Monday we come in and look at the DHCP servers or look at the backups or look at the email servers, then very quickly, by the time you scale that up to 75 different things, you'd get to the point where we literally spend all of our time looking at stuff and not actually changing anything. So generally, one of the goals that we have is that we only want to have to touch things when we want to change them. There's also quite a lot of interactions with external systems, whether Microsoft, Salesforce, a million other providers that we work with. But of course, the usual rules of systems apply, and that's that they do change. Sometimes it's because we want them to change. Sometimes it's because things sort of gently drift over time. APIs exposed by external providers change, software packages update, the new version behaves differently to the old version. Or you've sort of made a change in a bit of a hurry and you've forgotten to update the docs. And so, of course, that goes inevitably along with comments in code are always out of date, documentation on systems is always out of date. That doesn't mean it's not useful. We've got a whole bunch of documentation that we do use. It is really useful. But you sort of have to assume that it's a little bit separate from the system that backs it. And of course, we need to be able to recover pretty quickly when things catch fire. So unlike a product that you build, you ship it out the door, and generally speaking, If a customer's installed that version and it worked for them last week, it'll probably work for them this week. With a lot of infrastructure, you start it running, it will at some point tend to break, whether you deliberately change anything or not. So you want to speed up how quickly you can get back from that break, because often if something is broken, it's kind of affecting people around the building or affecting our customers. If Redgate.com goes down, then effectively no one can give us money. And if no one can give us money, it doesn't take a very long time before our bank account goes from a nice big positive number to a not so nice less positive and then negative number. And that makes everyone sad, especially at Christmas bonus time. So yeah, we sort of have all of these systems, and it turns out that there's a big spread in how long you can afford for something to go down. And if you think about the business, actually the ability to accept money is one of the things that becomes most critical most quickly. If we can't take payments on our website, then very quickly that has a substantial unrecoverable impact on the bank balance. If we can't ship a new version of a product, we can probably live without that for a few days. Clearly not ideal, we're not getting value into customers' hands, but we can still sell what we have got at least. So when something does break, we want to figure out what's gone wrong as quickly and easily as we can, and then we want to be able to recover it. Come on to the diagnosis bit a little bit later. So how do we make recovery easy? Again, 75 different things that we're doing. You can't rely on remembering how to do it, because chances are last time you did this was a year ago, hopefully. Chances are the documentation's out of date, so let's not rely on that either. Instead, let's automate as much as we can of it, within reason. We sort of had this discussion recently where it's like, oh, okay, should we have our goal as automate everything? And that's not quite right, because if you spend a month automating something that takes you 5 minutes to do it manually, and you do that once a year, then you can kind of work out the payback period on that. On the other hand, there's sort of the other benefit to automation, which is that if you always deploy something automatically, and you get used to doing that very regularly without caring too much about it, then suddenly that makes it much more likely that it'll work the next time you do it. So it used to be that sort of sysadmins had this kind of proud thing, oh, this server's been up for 1,000 days. Yeah, it's been up forever, it's so reliable, it never crashes, it never goes down. Look at the uptime on that. And that used to be a mark of pride, and actually it's terrifying. Because if something's not been rebooted for 1,000 days, what's the probability it's going to come back up in the same state when you do reboot it? And that's horrific. If it's the sort of thing where if you haven't tested your backups, how do you know they're good? If you haven't tested rebuilding a system, how do you know that the procedure to rebuild it is still going to work? Whereas if actually you get to the thing of how do we know that the next build system that we build is going to behave in the same way as we think it is, well, if it was done yesterday, then that's a really strong guarantee that that's going to do what you think it's going to do. At the same time, there's a risk if you do that all the time and make that really easy that you don't dig into what caused a problem in the first place. So being able to throw things away really quickly and use that as a way of getting back online is really useful. On the other hand, you do need to be able to then look back after the fire's out, after everything's back to life, and say, right, okay, what caused us to need to do that as opposed to just being able to do it? So generally, as a sort of strategy for this, we tend to go for the sort of X as code for all X. It's a very sort of nice, trendy way of describing it, but what it actually means is that we can source control everything. It goes into Git. It goes in as human readable, for some value of human and readable, but basically it goes in as text. And once it goes in as text, you can revision, you can version everything. You can see what's changed. You can branch it. You can say, okay, we're going to put together this set of changes, so let's do that on a branch, spin up a test system, recreate that, make sure that it works like we expect it to. It means you can diff everything. So When someone comes to us and say, oh, right, TeamCity's behaving differently this week compared to last week, you can go and look at the code that deployed those build agents and say, well, that's what's changed, and very quickly nail down the problems. Of course, you have to be, the amount that you can do that diffing is limited by how much of this you source control. So the classic thing is if you say, okay, well, when I build a build agent, go and install NuGet. If you just say go and install NuGet, then you'll probably get the latest version of NuGet, at which point when they do a release of NuGet 4.9, which behaves differently to 4.7, and stuff breaks, sorry, then you're surprised and that doesn't show up in your diffs. So actually we're quite aggressive in a lot of the infrastructure side of things in pinning things to versions, which is an interesting one because you can kind of take two approaches. It's like, do you always take the latest, or do you specifically take new versions? And that's a little bit of a trade-off. We tend towards the pin a lot of our immediate dependencies, but that's a very sort of transitive thing. So that's how we aim to move is towards everything in source control as far as we possibly can. That isn't always possible, especially with third-party systems. We also want to obviously be resilient. The best kind of failure is one that no one notices. And yeah, the number of times things have failed, and hopefully no one in this room apart from me would have known that, is quite high. If I can go and shut down a web server and every single request still gets serviced as quickly, then that's great. Because first of all, it means when one of them gets turned off without me expecting it, then no one notices either. It also means that, of course, I can do my work, I can make changes during business hours. 4 of us are based in the UK, but we've got folks out in Australia at UTC +10, we've got folks over in Pasadena at UTC -8. That pretty much means that during the week there is no time that we don't have people working. At the weekends, a little bit more flexibility, but certainly our customers are still there. If you look at the Google Analytics real-time graph for SQL Server Central, there's definite peaks and troughs, but even at the quietest time, which is at sort of 4 in the morning on a Saturday, you've still got 100 people actively browsing the site. So yeah, you want to be able to make these changes without having an impact on people as far as possible. And of course, there's the sort of the larger scale failures of Redgate as a company needs to be able to survive. You have the sort of metaphorical thing of Newnham House catching on fire. That's obviously a little bit extreme, but much more likely Newnham House not having any water, or not having any electricity, or having slightly excessive panels of glass. All of those things have happened. And we still need to be able to carry on trading as a business. We still need to be able to take money to ship software, to build software, all of that, whilst those things happen. In terms of how we do that, it's generally via redundancy. We have multiple copies of things. As far as we can, we prefer to do that at the application level. Now, sometimes that's easy. If it's a web server, generally speaking, you just run multiple web servers. You put them all behind a load balance, or actually you put them behind 2 load balancers, because what happens if your load balancer fails? You then put those 2 load balancers behind DNS, which has some health checks, and that means that you can recover reasonably quickly from that. For things like SQL Server, you can run SQL Server availability groups. For other applications, you start getting bitten by things like licensing costs. So Confluence, the info site, has the ability to run redundantly. You can run 2 Confluence servers. Unfortunately, they want to charge us about £50,000 a year to do that. The number of times Confluence, recently, it went through a bad patch, the number of times that Confluence goes down and the cost of recovering it and accepting that 10 minutes downtime while we do the usual IT ops solution of turn it off and on again isn't worth £50,000 a year. So sometimes you just sort of say, okay, well, we can't justify that. What else can we do? For stuff that runs within Newnham House, we also have a disaster recovery site. It's basically a data center the other side of Cambridge, and we've got a nice bit of fiber between the two, and we just replicate the virtual machines. So any writes that happen to the disks in Newnham House, gets sent across the network, same rights happen to the disks over in the DR side. And that means that if we lose mains power and the UPS runs out of battery and everything like that, then we just turn on those machines over at the other side and things carry on. Generally speaking, that works for a bunch of stuff. Some stuff, you can't even do that. So the network switch that your computer is plugged into, like physically there is a bit of cable going from your desk to a network switch. If that network switch goes bang, then you know what, there's going to be some downtime while we take it out and put a new one in. And we just have to keep spares of that stuff. So where do we put things? We're not a data center. We are not Google, we are not Red-centric, we're us. And it turns out running a data center to the standards that you get from Amazon or from Lynx or from any of the big data center providers, that's really hard. Achieving 99.9% uptime, that's easy. You have like 45 minutes a month down. You have to be doing really quite badly to not achieve that. That, by the way, is the SLA given by almost all cloud providers. It's terrible. Thankfully, they almost all do better than it. And so that means that we say that nothing customer-facing should exist within any of our physical offices. Like, we should be able to close down all of our offices, and customers can still browse our website, they can still buy our products, they can still give us money. Similarly, Redgate people should be able to work from anywhere. Ideally, using the VPN as little as possible. We've not got there yet with that one. We're getting there gradually. So you'll have seen changes, things like TeamCity available now out without the VPN. Obviously, using GitHub, that doesn't matter where you are. And that's the goal that we're sort of working towards, is a little bit of a mindset change compared to how networks tended to be run 5-10 years ago. So okay, why do we have a server room? And if you've had meetings up on the top floor in the sort of sofa area, you've probably heard things. Well, we've still got about 1,500 network sockets in the building. Those still need connecting to the internet. And also, sometimes just being physically close matters. We've got 10 gigabits a second between a whole bunch of our things in our building. If you're building trade show laptops which require 100 gigs of VM to be copied around, guess what? That's a lot quicker when you've got a bit of fiber going across the room than it is when you're dragging it down from a few hundred miles away. Similarly, when we're building new PCs. So there's some stuff where it's just more sensible to have it running in the building. There's also the other bit, which is money. One of our build agents, of which those are a few examples. One of those to buy costs about £1,000. Of course, it uses some electricity, so if you do it over 3 years, it's about £1,500. That gets you a 6-core, 4.2 gig CPU, a bunch of really quick storage, a bunch of RAM. And so TCO over 3 years is about 1,500 quid. Why don't we just run it in the cloud? To get the same thing in Amazon EC2 is about 7 times as expensive. Now multiply that by 30. That's a lot of bacon rolls in the morning. And for this stuff, what benefit would we have doing it in the cloud? Actually, very little. You have the resiliency thing. What happens if Newnham House burns down? Okay, so we take the 30 of these that we have and we spread them. So we've got half in Newnham House, half of them over at the DR site. Okay, if the building burns down, your builds take a little bit longer to go through. Is that going to be the highest priority for anyone? If that happens, we go down to PC World, we buy a bunch of new desktop PCs, we stack them up in the corridor of some rented office, we turn them back on, and now your builds are fast. It's commodity hardware. It doesn't matter. That'll take us no time to do. So actually, there's a financial argument for doing that in some cases. It wouldn't be sensible for us to run the Redgate website like this, because there the resiliency is absolutely critical. In other cases, stuff only lasts for a short amount of time. If you want to spin something up for a week, then you don't want to have that £1,000 hardware cost where you can just pay Amazon a small amount of money for a small amount of time. The flexibility that you get with public cloud providers is massive. So it's really about making the right decision for the situation. Okay, so how do we actually deploy stuff? You've probably seen sort of infrastructure as a service, software as a service, platform as a service, pick any letter of the alphabet as a service. Infrastructure as a service is basically virtual machines, or things what look like a computer. It turns out the cost of those scales really, really linearly from a tiny amount. So you can go and buy a EC2 T3 Nano that gives you a fraction of one CPU core with half a gig of RAM. That costs you about $3 a month. Like, there is nothing that we run that is worth less than $3 a month. And that scales all the way up to some ridiculously large thing with about 200 CPUs and 4 terabytes of RAM that'll cost you an eye-watering amount per hour. Combine that with virtualization overhead being really low. When I say really low, like unmeasurably low. If you look at the technology that's now available, the cost of running something on virtual hardware rather than physical is pretty close to zero with a couple of exceptions. So actually for us, running stuff in containers often doesn't make a lot of sense. Like the advantage of, okay, we can speed these, we can spin these up really quickly. Well, you know what? Stuff doesn't change that often. Or the advantage of we can run lots of containers on one machine. Well, why not just run lots of smaller machines, and then they're better isolated? Software as a service, some of it adds loads of value. Office 365, we never have to run another Exchange server in our lives. Thank goodness for that. Slack, Zoom, yeah, all of these, Salesforce, HubSpot, millions of systems that add a huge amount of value that we just don't need to worry about. Platform as a service, a lot of the added value is frankly a bit dubious. Like Amazon RDS or Azure SQL Database. It's like, hang on, how long does it take you to install SQL Server? If you automate it, about a minute. It doesn't really add a great deal beyond that. In terms of how to make these easy then, give me some files. Let me run an application. That's the easiest thing. .NET Core makes this amazingly easy. It packages up all the dependencies at an application level. You just unzip something and run an executable. Why not do that? It avoids things being a black box. If you really need to ship a whole machine, we've got standards for that already. But again, it removes the ability to diff things. It removes the ability to branch things. It removes the ability to see what's going on inside of something. But don't forget, our time is also money. So you don't want to work to the lowest common denominator in all of these things, whilst at the same time remembering that the world changes. Rackspace were the first cloud provider to run SSDs in their virtual machines. That made a massive difference. Then they basically went out of that market. Azure were the first ones to market with Azure websites. That was a game changer at the time. Actually turned out not to be so much. EC2 currently leading the way for infrastructure as a service. Is that going to be true in 3 years? Probably not. If you build on standards, then you're not locked into a given platform for all time. It's going to cost you something to move to someone else. If it costs you nothing, you've probably done a load of work you don't need. But if you build on industry-wide standards, HTTP, NFS, DNS, WS Federation, OpenID, then you can actually move fairly painlessly whilst being able to take advantage of a lot of the platforms and features as well. I'm really running behind. So how do we make all of this fit together? Git and Octopus, I'm kind of guessing you know. DNS control. Service discovery, that's the thing, right? DNS fixed it 30 years ago. Seriously. If you want to know how to locate a service, create a DNS record. You can do that in any vendor. You can do it with any network has this infrastructure already. DNS control lets us write it as code. That's a JavaScript-based DSL. You can check it in. If you send us a PR against the redgate.com DNS zone, it'll get automatically deployed. Today, it goes on to Amazon Route 53 as a DNS service. Turns out it's not worth running your own DNS servers. But if we want to move to someone else tomorrow, you change DNS provider R53 to DNS provider Dyn or Bind or Azure or anything else. We can do that. Razor effectively does the bottom end of building machines. This gets you from bare metal or from a an empty VM up to a provisioned operating system. You've probably seen this if you've ever blown up any of our test or build agents. Effectively, it reboots it, boots it off the network, deploys Windows, gets it on the network, and installs Puppet. That suddenly means that we're at a place equivalent to running stuff in EC2. Puppet takes a machine and declares what you want it to be. So in this case, I want to say a DNS server is installed, a virtual IP address is registered, and I want a bunch of DNS zones. Which DNS zones do I want? Oh, those ones. Okay, if I now have another DNS zone I want to serve, I add one line to that file, and it will do whatever needs to be done. It means that we can make small changes very quickly. We're not rebuilding entire machines every time. It's just an incremental deployment. And we can safely make large changes out of the way on a different branch. There's no binary black boxes. All of this stuff composes together, and you can reproduce it in a different environment if you need. Very quickly, certificate management, more generally secrets management, although a lot of that happens in Puppet. HashiCorp Vault is a box of certificates. Today, we issue them via Let's Encrypt. Tomorrow, who knows? None of the edge systems care about this stuff. We have one bit which issues the certificates. Puppet pushes them out to the machines. Neither of those things know about the other. On security, we've got loads of different systems. Some of them are old, some of them are rubbish. Something will get compromised. How do we limit the damage when that happens? And finally, when something does break, let's make it easy to diagnose. Standard network technologies, then you can figure it out. Don't use overlay networks, please. Logging and monitoring, Simon's already talked about. Things fail in really weird ways. I'll leave you on this. This was the other weekend. One of our switches decided that because we had the temerity to SSH to it, it would throw 10 gigabits a second of traffic into the core of our network and keep doing it. There was no reason for that whatsoever, but it happened. That was the graph that we used to diagnose it, and we went, oh, that's what's happened, pull that, turn it off and on again, and it works. We've now replaced the switch. So, but it was only by having all of this stuff that we had the confidence to be able to do that. I think we're a bit limited on time for questions. Grab me afterwards, grab us on Slack, IT Ops in the core channel is generally a good one, or just come and chat. Thank you, everyone.